Lots of the work in this paper uses calculus, but it doesn't use just normal calculus that you might have learned before. It uses multivariable calculus, or sorry, not multivariable, like a geometric calculus, but they call it space-time calculus because it's geometric calculus, but only in the context of space-time. So here's how they go about doing it. This section is called field and integration because it talks about how fields are constructed and how directed integration can be done over fields. So first, the STA, the mathematical framework of the STA needs to be extended. It needs to be extended to allow for calculus. So there are two main steps. The first step is to just take a flat, what do you call it? A space-time manifold. So, for example, I've already drawn one. So you just take this. This is a space-time manifold, and it just exists there. And the space-time manifold has points. And the second step is to assign a singular geometric algebra and specifically G13 because this is the space-time algebra. So it's to assign a single geometric algebra G13 and then have it depend on space. And then you assign that to each position, say, and this is space-time position. We have the x components here. And these are on the manifold. So what you do is you just take this, and then at each point here, so like starting here, you take this point and you assign, let's say that this is position x1, then we assign this G3 on x1. And then say that we take this next point, or we would take some other point here, and go here, and then this can be G13, and then this is x for maybe let's say A, and you have a point there, and you can do that for every single point on this manifold. Every single point can have a geometric algebra at this point. So what this does effectively, the space-time algebra, acts as a field. Acts as a field on, or I'll call this field G13 of x, on the manifold. And so essentially your Clifford algebra now changes in space the values that it takes. It's still the same algebra, but the values taken by it change. So it's effectively a field. This means, so thus multivectors are fields. So a multivector field here is within the geometric algebra field. Now, if you were to consider all of these together, there's a technical mathematical term for this. It's called a Clifford fiber bundle, and essentially what that means is that there's a local space at each point, and then there's a big space. So in the big space, you have position assigned to each local point, so that when you're in the big space and you go to a point, locally there's something there, and you have that at each point. For here, the big space is space-time, and when we go to a point, the local space is the Clifford algebra or the geometric algebra. And so because of that, it's called a Clifford fiber bundle. That's what the definition of that is. So this is what allows for calculus to be done, is by considering these as a field over space-time. Now, if we want to do directed integration, we can say that for all x on the manifold, so for every position on the manifold, there exists a corresponding infinitesimal k volume. And this is defined as dk of x is equal to the magnitude of dkx times ik, where this ik here is the unit, is the unit k blade for that space. So it would be a k. This would be a k volume. This could be a k volume right here, but it's also a blade. So an example of that is to let k equal 4. So that's the maximum dimensionality of the space-time algebra and the space-time manifold. So you end up with d4x, which is equal to the magnitude of d4x times the the pseudoscalar, or the unit k blade for that, but that's just the unit pseudoscalar, which is just gamma 0, 1, 2, 3. And that comes from the fact that you take this vector, this infinitesimal vector, wedge, this infinitesimal vector, wedge, this infinitesimal vector, wedge, this infinitesimal vector. And so these differentials are actually just elements of the algebra, but they have the infinitesimal magnitudes that are required within summations and integration. So you can then have a directed integral. So directed integration. And in this directed integration, you're taking the integral over some k volume. So this is a volume of dimensionality k. So it could be, if it's one dimension, then it's a line. If it's two dimensions, a plane. Three dimensions, a volume. Four dimensions, a hypervolume. So that's the idea. That's what this is. It's telling you to integrate over that region. And then you have some multi-vector function that depends upon x. And then you have dkx. And just for simplicity's sake, or not simplicity, but to expand this out, this is equal to m of x. Then you have the magnitude dkx. And then ik. But this right here is just a magnitude. So you can just move everything to the left that has a magnitude. So you can just say it's like this. And this would be a directed integral, where the product between this multi-vector function and this k, what's it called? This k blade, this is just the geometric product. And it's then being summed up for every infinitesimal volume here. And it's being added up in this integral. So then how would we do scalar integral? So another way to call this is, you can call this scalar integration. So this is normal integration, undirected. So you want to take the integral just over the magnitude of this, so you want this right here to be a scalar, not have any magnitude. So you take the k vector infinitesimal, and then you multiply by the inverse of the volume infinitesimal, or the blade, because of this definition here. If you just multiply by the inverse of this on this side, then you get this, and that's exactly what this is. So then an undirected integral would look like this. So you could have vk, then some multivector field, and the magnitude dkx. Or you could have, like, for example, if you wanted to find the volume of the region, so you wanted to find the volume of vk, then you could just take the integral of the region vk and this right here. This is how you do directed integration, and this is how you do scalar integration or undirected integration.